want to talk about gravitational field today. I know the other day we talked about universal gravitation, and universal gravitation leads to this cool thing called a force field, or a field force, really. Gravity is one of the four fundamental forces, and it's a field force. That means it acts over a long distance of space. It doesn't have to be in contact, right? And that's what Newton's law of universal gravitation said that was so incredible. It said that in order for gravity to pull on stuff, the two objects don't have to be touching. They don't even have to be that close. Gravity can act over an incredibly large distance. Gravity acts over any distance, and it just depends on the two masses and how far apart they are, and then we use this universal gravitational constant g to get it into units that we can understand. So m1, m2, and r, where r is the distance between m1 and m2, it's the distance between the centers, right? So when we're using planets, if you've got somebody standing up here, that doesn't mean r is 0. R is measured from the center of the planet to the edge of the planet, right? This is r. So that's kind of important. Anyway, this is Newton's law of universal gravitation, and what it describes is how strong the force is between two masses at any distance. Well, what if we're interested in the strength of the force at lots of different spots? Okay? Then what we're really interested in is the gravitational field, or the strength of the field at a whole bunch of different locations. And the way we talk about fields is we draw lines that represent the field. So these are field lines, and they point in towards the center of the mass. They point in because this is an attractive force. All these field lines are going in towards the center of the mass where the force is actually being pulled, right? Okay. Now, these lines represent the strength of the field at all these different points, as well as the direction of the field. Okay. And then you can see close to the surface, we have this many lines in this much area. But far from the surface, out here, we still have the same number of lines, but they're trying to cover a much greater area. So it's like this field gets spread kind of thin. And so that's kind of the representation of this m1, m2 over r squared thing. As r gets bigger and bigger and bigger and bigger, the force of attraction gets smaller and smaller and smaller and smaller and smaller. And so this sort of equates with Newton's law of universal gravitation. But it allows us to find the strength of the field if we consider a test mass, right? So I'm going to call this my central body. This could be Earth, this could be the Sun, this could be whatever. It's the big mass in the middle that we're worried about. If we want to know the strength of the field at this point, what we do is we consider a test mass. Okay, this is m1, and this distance from here to the center, this is r. Okay, and we say, okay, well, let's consider just the strength acting on this mass. Okay, now, if this was Earth, we would say that that object has weight, and we would calculate the force acting on it as its mass times the acceleration due to gravity, g. But that's identical to the force that's acting on it because of universal gravitation. So we're going to take the mass of the central body times its mass divided by r squared, okay, and multiply this by g. Now, this, of course, depends on the mass of the object. It's in both of those equations. And since we want this to be true for any mass, not just this mass, what we do is we divide every part of this equation by m. So I divide f by m, I divide m by mg by m, and this thing by m. Okay, and that cancels here, cancels here, cancels here, cancels here, and, well, it doesn't cancel here. So I'm left with the force per unit mass is equal to g, which equals the mass of the central body times the distance between the two objects, or the distance out from the central body, squared, times the universal gravitational constant. Now this is little g, this is big G, they're different. Little g is actually describing a force per unit of mass, right? It's measured in newtons per kilogram. But if you think about what that means, a newton per kilogram, okay, a newton is a force, and force is mass, which is kilograms, times meters per second, which is acceleration. If you divide that force, a newton, by a kilogram, you're left with meters per second per second. So what the strength of a field in newtons per kilogram tells you is the acceleration of an object due to gravity at that point. Okay, so I'm going to write that out. Field strength is the same thing as the acceleration. Okay. Now, of course, this leads us to the conclusion that the acceleration due to gravity is not constant. Okay. For things near the surface of the Earth, we know we've measured it to be 9.8. But for things way out here, it's not that big. It's going to be much, much, much smaller. Okay. And we're going to work a problem real quick about the International Space Station, but that's kind of an interesting thing, okay? But it allows us to calculate 9.8 and where it comes from. Okay, why do all objects accelerate with 9.8 meters per second acceleration if they all have different masses? Well, it's because it's not dependent on mass of themselves, it's dependent on mass of the Earth, right? And you can see that in this equation. F equals m1 times mass of the Earth, if that's what we're on, divided by r squared times g. That's the force of attraction between an object and Earth, where this is basically the radius of the Earth. But that's equal to Newton's second law says mass times acceleration, ma. Since m is in both sides of this, it cancels, and we see that the acceleration cancels, or the acceleration is what's left. Mass of the Earth, mass of the central body times g over r squared. So this determines acceleration, not force, right? The other part that we need for force is this mass, right? If I have a mass out here and a giant mass out here, this one feels more force, this one feels less force, but they're going to accelerate at the same rate. Their acceleration is constant. Okay? Now, let's use this two ways. Okay, first we're just going to verify our 9.8 meters per second per second. Okay, the acceleration due to gravity on the surface of Earth. G on Earth's surface. Okay, if I'm going to do this, then what I want is the equation for field strength, G, equals the mass of the Earth, because that's what I'm talking about, times G, the universal gravitational constant, divided by the radius of the Earth, squared. Alright, so I have 5.97 times 10 to the 24th, and this is going to have a little bit of air in it, times 6.67 times 10 to the negative 11th, divided by 6.38 times 10 to the 6th squared. And you can work it out. Now, why is that radius not 0 even though we're on Earth? It's because, again, it's measured from the center, not from the surface. Okay? So this equals about 9.8 meters per second, give or take a rounding error too. This is g, the acceleration due to gravity, but it's also equal to 9.8 newtons per kilogram. That's how much newtons of force act on every kilogram of matter on the surface of Earth. Okay, so let's think about astronauts in the International Space Station. Okay, the ISS orbits at 370 kilometers above Earth. Now, I'm always blown away by how small that number is. Okay, and I know 370 kilometers is a long, long ways above Earth, but compared to Earth itself, this is a very small distance. Earth has a radius of 6,380,000 kilometers, or 6.38 times 10 to the 6th meters. Okay, so 6 million meters. The International Space Station is like right here. Okay, this is 370,000 meters. Okay, so it's just this last little bit again. Okay, so when we're out here, what we use for r is the radius of the Earth, plus this distance between them, plus 370,000. Okay, and that gets us the radius. So if I want the acceleration due to gravity up here, or I want g, the field strength for the International Space Station, what I'm going to do is I'm going to take, I'm going to take mass of the Earth, 5.97 times 10 to the 24th, times g, 6.67 times 10 to the negative 11th, divided by this distance, 6.38 plus 37, so 675,000 squared. And if I work that all out, remember g is 6.67 times 10 to the negative 11th, then you'll come up with a number that's actually almost exactly g. It's like 8.74. 8.74 newtons per kilogram. Okay? So why is it that an astronaut in the International Space Station feels weightless when there's actually almost Earth's gravity still acting on him? This is 8.74 instead of 9.8. Okay? Well, the reason is what's actually happening. Right? This thing is being accelerated towards the center of Earth, but it was also given a very large velocity this way. So as it orbits Earth, okay, its inertia wants to keep it moving in a straight path, and gravity wants to pull it down. And so it's falling towards Earth, falling towards Earth, falling towards Earth, falling towards Earth, but it keeps missing. Okay? So it's in a perpetual state of free fall. And when you're free falling, you feel weightless because nothing is pushing up against you. Okay? And so it's not that there's no gravity in space. There is lots of gravity in space. When you're orbiting another planet, you do not feel it, right? We're in free fall around the sun. We don't feel the pull of the sun because we're orbiting around it. How big is the sun's gravity where we're at? Okay? Let's talk about that. The field strength of the sun. Okay? And so G from the sun where we're at. What we need is the mass of the sun. We need G, and we need the distance R from the sun to Earth. And I can look all this information up real quick. It's all in the book. I think that's even on the front and back cover. But the distance between the Earth and the sun, this distance right here, oh, by the way, we have to square it. This distance, Earth-Sun distance, is 149.6 times 10 to the 9th meters. Okay, that's a lot. We're a long way from the sun, almost 150 kilometers, 150 million kilometers away. And then we also want the mass of the sun. The mass of the sun is 1.99 times 10 to the 30th kilograms. 1.99 times 10 to the 30th kilograms. Okay, so the sun is fairly large. All right, so let's see, how big is G? So I have 1.99 times 10 to the 30th times 6.67 times 10 to the negative 11th divided by 149.6 times 10 to the 9th squared. And if I work this out, we get 0.00059, which is incredibly small, right? That's a really small acceleration, or a really small strength, newtons per kilogram. Why is that big enough to keep the Earth in orbit around the sun? Well, if you think about it, it's because the mass of the Earth is huge. If you multiply this by the mass of the Earth, 5.97 times 10 to the 24th, you end up with a whole bunch of force that is keeping us in orbit around the sun. But it's also why we don't really feel an attraction to the sun. We don't have much mass. We're not going to feel that. Okay. Plus, we're free falling around it, so we're basically floating anyways. Okay. All right. So we're going to work a couple problems today. You're going to work a couple problems today where you actually have to calculate the force of attraction between things, or the strength of a field at different points. So that's pretty straightforward. Remember, field strength, G, is given by mass of the central body times capital G, which is 6.67 times 10 to the negative 11th, divided by r squared. And, of course, the force of attraction between any two objects with mass is m1, m2 over r squared times G. This one is a force, it's measured in newtons. This one's the strength of a field, it's measured in newtons per kilogram, or meters per second per second. Now, one more thing I want you to think about. Okay? When you're on Earth, we think about things as having gravitational potential energy. We lift it from here, up to here, we've given it more energy because it wants to fall back to Earth. We've done some work this way, Earth's gravity has done some negative work, and so it'll release energy as kinetic energy when it falls back down. What if we get that object way out here? Okay, does it still have gravitational potential energy? We think, well, it should have tons because it's got to fall for so far. Except if it's far enough away, the force of attraction is really small, because the force of attraction is proportional to the distance squared, and as this distance gets big, this whole fraction gets little. Okay, and so it turns out the maximum potential energy that something can have actually doesn't. This is where negatives come into play. Okay, we got to remember that energy is not necessarily a vector, but it does make sense to talk about negative energy because it's the work that's done. The work done to lift something is negative. Okay, the work done to lift something is negative because your motion is one way, but it's against the force of gravity. So gravitational potential energy is considered to be a negative energy when you calculate it using this equation, right? Oh, and by the way, to calculate it using this equation, work is force times distance, and that's change in energy. So if I multiply this by r and I multiply this by r, then what I get is the gravitational potential energy, U, is given by negative mass of the Earth, okay, mass of the object, rg. Okay, so this actually kind of makes sense. It's a negative energy because the force that's pulling it down is against the distance that it had to move to get up there. Okay, which means the further and further and further and further away you get from Earth, okay, the closer you get to zero U, zero gravitational potential energy. That's another abbreviation for it. As you get closer to Earth, this fraction gets bigger, but since it's negative, the value is actually getting smaller. So the gravitational potential energy decreases even though its magnitude becomes bigger. I know that's crazy weird, but essentially what this allows you to do is use the law of conservation of energy, which says the kinetic energy plus the potential energy, U, at any point has to be constant. Okay. Well, if we want to give something enough velocity to get away from Earth, escape its pull, then we need to get it way out here. And what we can say out here is U equals 0. Okay, there is no gravitational potential energy out here. It's too far away. So we're basically letting R equal infinity. Okay, we've got it an infinite distance away. And since all we want to do is get it away, we can say that its velocity is also equal to 0. So we don't care if it slows down and stops at this point. We just don't want it to come back. Okay? And so what we're going to say is okay, this constant is really 0 because we're going to say no kinetic energy, no potential energy. So we have the kinetic energy, 1/2 mv squared, plus this negative me m over r has to equal 0. And so we can see that the escape velocity, or the velocity required to get something out of Earth's gravitational field, away from it, is given by the square root of the mass of the Earth times g, oh, I left that in my equation, divided by r times 2, right, got to move the half over, square root it. This is what's called escape velocity. And so it really gets down to an energy thing. How can we get something to fly past Saturn? How can we get it to break Earth's gravity? We have to give it an escape velocity. We have to give it a really high speed. Okay? Alright, I will get some problems for you guys. Let me know if you have any questions.